This is lesson 4.3 on ratios and equivalent ratios. Before watching the recording, please make sure that you have a graph sheet of paper in front of you. You may use your math journal, so you may be online, or graph paper in your math journal. Or if you do not have either of those writing materials, you can use a sheet of paper to jot down the notes in this video. Please also make sure you have a pencil, some different colored pens, and perhaps a highlighter as well. If you need to pause the recording to get those items, please do so now. So I'm going to continue on. Make sure you write down today's date and then the title, which is 4.3 ratios and equivalent ratios. So let's just review some definitions to start off with here. As you watched the Brain Pop video the other day, you were introduced to the concept of ratios. And a ratio is a comparison of two or more quantities you can have either a part-to-part ratio or a part-to-whole ratio. So again, a ratio is a comparison of two or more quantities, and you can have either a part-to-part ratio or a part-to-whole ratio. So let's review this concept of ratios. So I'm going to get my different colored pens out. I'm going to use blue here, and I'm just going to draw a diagram here. So I'm just going to do some random blue circles. And you can do the same. You don't have to use, well, you should probably use blue just to be consistent with the colors that I have here. And then I'm going to use, let's do purple here. I'm going to do purple triangles. Try not to make this too difficult on myself here. And this is the best way to illustrate your understanding of ratios. And let's do green. Let's do green squares within the squares here. Okay, so there we go. There's our diagram. Now, we look at this diagram here, and I'm just going to expand or zoom in on the screen here for a second. So we look at this diagram, and we want to build certain ratios out of this diagram. So here are some questions I'd like you to answer, and I invite you to try and answer these questions first, and then you can replay the recording afterwards just to check your answers, because it is good to check in and see if you understand how to build these ratios. Remember that order matters with ratios, as in you have to keep the same order in which the quantities are described. So for example, or the quantities are named. So here's your first question. I'd like you, what is the ratio of blue circles to purple triangles? Okay. Second question. What is the ratio of green squares to purple triangles? And then the third question I have for you is, what is the ratio of green squares to all shapes? Okay, so I encourage you to pause the recording right now and figure out the ratios for each of those three components of the diagram. So I'm going to continue here. So remember what I said before, that order matters and that the ratios have to be consistent with the items that are described. So for example, we're looking at number 1 here. I'm going to look at the blue circles and I'll just be consistent with color here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got, and I'm just listing it just underneath, 10 blue circles, 2. Now, the preferred way to express a ratio is the colon method or the dot dot method, as I call it. The word TO is often used as well. Sometimes you'll see it expressed like it looks like a fraction, but get into the habit of using the colon method in terms of expressing ratios. So we know that there are 10 blue circles, and I'm being consistent with the order. To purple triangles, we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the ratio of blue circles to purple triangles in this diagram is 10 to 8. We look at the next one. We've got green squares to purple triangles. Green squares, we've got 1, 2, 3, 4, 5, 6, 7. So we've got 7 green squares, 2. Purple triangles, we already have the amount of purple triangles as expressed in the previous question. So we've got 7 to 8. Now, again, we have the part of the answer done for number 3. We've got green squares to all. We know that there are 7 green squares to all shapes. So we just have to add up 10 plus 7 plus 8. So 10 plus 7 plus 8, which would give us 25. So to all would be 25. Because that is the amount of all of the shapes. Now, let's go back and categorize each of these types of ratios. So in a different color, preferably, I'm going to do pink here. I'm going to say here, for number 1, ask yourself, the blue circles to purple triangles, what type of ratio is it? Is it a part to part or a part to whole? So you're correct in saying it's a part to part. So I'm just going to label it here, part to part. Number 2, green squares to purple triangles. Ask yourself, is it a part to part or a part to whole ratio? It is another part to part ratio because you're comparing 2 different parts of the diagram. Now finally, in number 3, if you look at green squares to all shapes, it's 7 to 25. We know that that's going to be either a part to part or a part to whole. So ask yourself which one it is. And it would be a part to whole because it's comparing a part to the whole. Okay. So those are how ratios can be formed if you're looking at a diagram, for example. If you're asking yourself, how are ratios used in real life? If you think about in the Brain Pop video, I believe they talked about, coming up with solutions for cleaning. So, for example, if you have a cleaning solution and you want it to be more strong, you would use more of a chemical like bleach, and you would put maybe more drops of bleach in a solution compared to how much you would normally put in it to make it more strong or to make the cleaning solution more powerful. You often see ratios in baking and in cooking as well, and we'll get more into that later. I will give you one problem at the end of this video to work with as well, but I do want to move on to equivalent ratios. Okay, so equivalent ratios is something that you'll be working with more in this lesson with the activities after this video. So jot down the definition of equivalent ratio. Now equivalent ratios are in the name, so they are equal. So they are equal ratios, and they behave the same as equivalent fractions. But ratios are not fractions. okay? But the math behind trying to figure out equivalent ratios is the same as how you would approach finding equivalent fractions of a number, which we dealt with earlier in the unit before spring break. So let's start off with some examples here. So say, for example, if we had a ratio 6:2, okay, and I asked you, try to find an equivalent ratio of 6:2. Well, I know that if I'm thinking of an equivalent fraction, I'm basically multiplying both sides. Or if you're talking about a fraction, you'd think about the numerator and denominator. But instead, we refer to it as both sides of the ratio. You always multiply it by the same number. So if I want to double this, say I multiply both sides of the ratio by 2, I know the equivalent ratio of 6:2 would be 12:4. Okay. Now, again, the same deal. Like, I don't always have to multiply. If I can reduce the fraction and keep it simpler, I could also divide both sides of the ratio. I can go 2 divided by 2 and 6 divided by 2 if it's possible. So 6 divided by 2 would be 3, and then 2 divided by 2 would be 1. So an equivalent ratio of 6:2 would also be 3:1. I want you to note important things here. So notice that we're always multiplying or dividing both sides of the ratio by the same number. Okay, so we'll jot that down in a note below. So to find an equivalent ratio, multiply, and this is where it behaves very similarly to an equivalent fraction, or divide each number, or each side of the ratio, I should say, by the same number. So remember things like LCM, lowest common multiple, or common multiples will come into play here again. As when we dealt with finding equivalent fractions or reducing fractions to lowest terms, there's similar ideas in that this is how equivalent ratios behave the same as equivalent fractions. It's really, really important, though, that you're always multiplying or dividing both sides of the ratio by the same number to get an equivalent ratio. So therefore, up here, we can conclude that two equivalent ratios of 6:2 would be 12:4 and 3:1, because we're multiplying both sides of the ratio by 2 in this first case, and in the second case, we're dividing both sides of the ratio by 2 in that case. Okay. Now, let's go with a word problem here just to sort of solidify the idea of equivalent ratios a bit more. I'd like you to write this down, and there is quite a bit to write down here. So let's just come up with an example here, just so that you can see how ratios are played out a little bit in a real life situation. Suppose you're making fruit punch, and you want to have certain ratios of certain liquids to be a certain way. So in a punch, so type of drink, a fruit punch, 2 cups, and this is where ratios play out into recipes a lot, of orange juice, are mixed with 3 cups of ginger ale. Okay, so question A asks, how much ginger ale is needed? for 10 cups of orange juice. Oops, keep doing that. And then B asks, how much orange juice is needed for 21 cups? It's a lot of punch of ginger ale. Okay, so it's the reverse of what A was asking. Okay, now you need to use ratio. Obviously, you have to show your work and use ratios to solve the problem. Now, if you want to attempt to solve both A and B right now, I encourage you to pause the recording and then check your answer when you finished. If you want a bit more guidance, another suggestion I have is you can just you can pause the recording and then check, and then pause the recording and then check your steps along the way. So I'll leave it up to you. If you want to just watch how I approach the solution, you're more than welcome to do that. So I'll leave those options for you so you decide as to what you want to do. Okay, keep doing that. Okay, I'm going to continue. So here's my solution. I'll just do it in a different color here. Let's go with purple. Okay, solution. Now, I would suggest that you set up the original ratio. The original ratio, if you look at the problem, in the fruit punch, I'll just highlight it. You've got 2 cups of orange juice. You've got 2 cups of orange juice, and you've got 3 cups of ginger ale. And the way I would approach this is I would always write down the original ratio and label what it stands for. So you've got, so that you're always consistent with the order, because again, order matters when you're dealing with ratios. It has to be consistent with whatever quantity is being named. So you've got 2 cups of orange juice, OJ, and then you've got 3 cups of ginger ale. So that's the basic ratio that you're dealing with, right? Now, for part A, it's asking how much ginger ale is needed for 10 cups of orange juice. I'm going to recopy the original ratio. So I'm going to go, 2 to 3. And then I'm also going to write down the reference. I know 2 stands for orange juice, and then 3 stands for ginger ale. Well, how much ginger ale is needed if we've got 10 cups of orange juice? So we know that we've got 10 cups of orange juice. We don't know what this quantity is. However, we can set up the equivalent ratio to figure out what this number is. So what I'm going to do is I'm going to figure out, well, how do we get from 2 to 10? We know we have to either multiply or divide to get equivalent ratios. I know that 10 divided by 5 is 2, so we have to multiply that side of the ratio by 5, because 2 times 5 is 10. Therefore, you can conclude that you have to always multiply both sides of the ratio by the same number, in this case 5. So we've got 3 times 5, therefore it's 15 cups of ginger ale for 10 cups of orange juice if you want to keep the same ratio of orange juice to ginger ale. So therefore you need 15 cups of ginger ale for 10 cups of orange juice. Now, you often see this, and again, I mentioned recipes before. So you would never change randomly the quantities of, say, if you were baking a cake and you were to double the recipe, you have to double all the amounts. You can't just double one amount and not the other amount, because obviously then your cake is not going to end up tasting the same or end up being the same if you've doubled the recipe. And this is where ratios come into play. So when you're doubling or tripling a recipe, you're actually creating equivalent ratios with all of those ingredients. So the same thing is happening with this fruit punch mix as well. Okay, for part B, it's asking how much orange juice is needed for 21 cups of ginger ale. Okay, we go back to the original mixture. So we've got 2 orange juice as a reference to 3 ginger ale, or 3 cups of ginger ale. So this time it's asking how much orange juice is needed for 21 cups of ginger ale. So we have the other side of the ratio now. Okay, we don't know what this number is, right? But again, we can figure out what number to multiply both sides of the ratio by. So we could go 21 divided by 3. We know that's 7. Therefore, we know 3 times 7 is 21. So if we multiply that side of the ratio by 7, we have to multiply the other side of the ratio by 7. So that means we've got 14. Sorry, I'm just going to rewrite this here. We've got 14 cups of orange juice to 21 cups of ginger ale. Therefore, you need 14 cups of orange juice for 21 cups of ginger ale. Okay, and that's how you can see an example of how equivalent ratios can play out in a word problem. I would always start off with the basic ratio that's presented in the problem, and if it's asking you for equivalent ratios, set it up so that you've got the quantities lined up and you've got the numbers lined up below. That's just a suggestion, but however you want to solve it is fine. So there's just one other note I want to cover with you, and that's generally how ratios are written. I kind of touched on it earlier in the video, but I want you to make note of it here because you could see it written in different forms depending on what resource you're using. Like I said, the preferred way to write a ratio is the 6, and then you've got the colon, or you've got the 2 dots there to 2, okay? And I'm going to just highlight that because that is the preferred way, is to write it this way, okay? Now, other ways you could see it written, 622, the word 2, because this stands for 2 when you state a ratio. Another way you can see it written is 622, but I would avoid writing ratios like this because it does look more like a fraction. Same with 6/2. Again, you could see ratios written that way, but it looks more like a fraction. I would stick to the first method when you're writing ratios. And that is the lesson on a review of ratios.